Welcome everyone. Today I will be presenting a fascinating paper that introduces a new model called LLaDA-MedV. We are going to look at how this model solves a major problem in current biomedical AI, autoregressive bottleneck, by using a technique called discrete language diffusion. Let's dive in. To understand the problem, we first need to look at our current standard. Right now, autoregressive models completely dominate biomedical AI, but they suffer from a lack of architectural patience. As you can see by the arrow hitting the red wall, these models rely on simple heuristics to control their length, which causes them to hit an early stop token and terminate prematurely. For instance, a baseline model called LLaDA-MedV only generates about 36 words on average, even if we ask 200 words in the prompt. As a result, these get clinically analysis that incredibly short and abrupt. Here is a matrix that perfectly contrasts the old paradigm with the new one. Autoregressive models generate text sequentially from left to right using unreliable heuristics for length control, which leads to those shallow outputs. They are fast but limited. On the other hand, the new max diffusion approach works through iterative denoising. Instead of guessing left to right, it explicitly pre-allocates space for longer answer. This makes the output deep and informative. Though it has some trade-off, uh, it is slower than the earlier one, but it is of higher quality. This brings us to the core of the paper, LLaDA-MedV, the very first biomedical diffusion language model. Unlike the standard models, it operates directly on discrete tokens rather than just image pixels, applying the language diffusion to understand medical visuals. Looking at the radar chart, LLaDA-MedV absolutely dominates the competitions, particularly in chest X-ray and CT scans. Overall, it achieves a notable 7.855% relative performance gain over the older LLaDA-MedV models. Let's look at a practical clinical example. When asked to describe opacities in the chest X-ray, the autoregressive LLaDA-MedV model gives a brief 36-word response, simply noting the areas of increased density. On the other hand, the LLaDA-MedV generates a detailed 166-word analysis. It breaks down the specific types of opacities like ground glass and consolidations, and even advises further to consultation with a healthcare professional. This shows that the diffusion models don't just describe what they see, they provide vital clinical context. Here is another clear picture of how the older model fails. When shown this split image and asked what imaging is on the right, the older LLaDA-MedV incorrectly guesses it is a B mode ultrasound, which factually incorrect and shallow. On the other hand, the LLaDA-MedV uh, correctly identifies it as an MRI image scan. Because it has explicit length control, the model has the capacity to explain how an MRI works and map the anatomical relationship back to the ultrasound on the left. So, how this model is actually built? The architecture relies on a three-stage training pipeline. In stage one, uh, in stage one is alignment, trained on about 600,000 image text pair using LLaDA 8-bit language backbone to establish the basic semantics. Stage 2 is the instruction tuning, which uses 60,000 multi-turn dialogues with inline mentions so the model learns how to converse. Finally, in stage 3, there is a task-specific fine-tuning on datasets like VQA-RD and SLAKE. This final stage is crucial because it ensures exact closed form accuracy and strict clinical rigidity. A, a critical finding in their methodology is what they call the initialization imperative. If you initialize the model with general vision weights, it's shown in the pathway A, it completely breaks down in biomedical settings, causing catastrophic token repetition where it just outputs the word the endlessly. General domain priors simply do not translate to medical semantics. Instead, we must use pathway B, domain-specific initialization, which successfully generates the medically sound output, like identifying the columnar epithelial T cells. Let's look at the engine itself to see how it writes. In stage 1, it starts with completely blank, pre-allocated canvas full of marks tokens. As it moves through reverse dynamics, it starts generating gases. The core mechanism is in stage 3, a low confidence remasking loop. The model iteratively predicts the sequence but purposefully remasks or erases its lowest confidence tokens so it can try again. It repeats this refinement until stage 4, where complete clinical clarity emerges in the final text. As computer science students, we know model building is all about managing trade-offs. This dashboard illustrates the operational trade-off for inference dynamics. The sampling step dial, or Z, is the master control dictating the balance between speed and generation quality. If we use 256 step, we get high quality score of 51.4, but uh, it takes slower 0.23 seconds per word. If we reduce the step count from 256 to only 16, it is blazing fast at 0.04 second per word, but the quality drops to 13.5. This system is not flawless, and this slide highlights a boundary in the architecture. When the desired response length is massive, but we don't allocate enough sampling steps, the model lacks the cycles to remux and refine its error. The diagnostic panel shows that this error state where the output degrades into endlessly repeating the word cells. The key takeaway for our future engineering efforts is that we must focus on adaptive step allocation to automatically balance efficiency and prevent this long form repetition. Despite being designed for long descriptive answer, the model still excels at strict short form questions. Look at these three performance styles. It achieves state-of-the-art closed form precision with 84.93 accuracy on VQA-RD and 92.31% on SLAKE and 95.15% on PathVQA. The authors highlight that while the architecture natively favors long-form depth, that targeted stage 3 fine-tuning we discussed earlier allows the LLaDA-MedV model to actually outperform the existing autoregressive baseline even on strict yes/no clinical benchmarks. To wrap this up, this paper establishes a new standard in biomedical AI. As shown in the central diagram, it combines explicit length control, iterative denoising, and clinical SFT to achieve the true unmasked clarity. The defining message of this work is that biomedical AI doesn't just need more data, it needs a totally different way of speaking. By replacing the frantic left-to-right guessing of older models with patient, iterative remasking of diffusion, LLaDA-MedV achieves the architectural depth required for true clinical reasoning. Now, thank you everyone for watching this video.